可以回忆一下，上一次我们是 review 了我们上一次是 review 了 probability 的基本的信息。在 towards end 的时候，我们讨论了一个process， 叫什么呢？叫 Poisson process。请问哪位同学还记得？对，还记得什么是 Poisson process？ 李老师，你要不要时间？你待会儿可能下半节好，那我们现在就开始喽。一下我们对上一次我们讲到Poisson process， 哎，谢谢。等一下，因为我们下节课再开始，所以还有时间。Bless you。这个是以后好。看看大家谁还记得 What's the Poisson process？ A Poisson process must be a point counting process. That's how we count. One way how we count. So ejection of particles and many things we're seeing and can be counted by Poisson process. First of all, I'm going to be there's the echo. So online folks, is everything going all right or there's an echo? 你们有听到回音吗？It's called with rate lambda. Is the following truth. First of all, when you start to count, t usually is the time. Initially, nothing happens. So this, how we normalize this? Yeah, very good. When we all says. And second thing, so fixed time, and we know any stochastic process, doesn't matter your counting process or any specific process, unless you are stochastic process will be a family of random variables. So fix each t, it will give us a random variable. Last time we defined, and as you can tell from the name, this is the Poisson process, fixed time. Shall we talk to Vicky? Thank you. So fixed time, this will follow a Poisson distribution. Do you guys have an example in your mind to that or something? And when you think about that, you will think about Poisson distribution. Yeah, exactly. Anything else?
一个路口在一段时间内的事故。
非常好，是 So number of car accident 在一个你特定感兴趣的地方 and per unit time 这个全都是 Poisson process。然后当 time 还有一个就我们常常天天都用 ，everyone has a phone。 So number of text messages you receive during a day. If T is the time, T is first day. Say average number of text messages you receive during the day, let's say 20. It depends on what you're doing, right? I'm just saying if that's 20. So it's a Poisson when T is the first day will be Poisson lambda equals 20. But the second day when T equals to 2 will be Poisson 10 times 2, 20. So keep going. Okay, so this will be each fixed T will be follow a Poisson distribution. And the third one, it has independent increment. So what this means, suppose here is S1, S2, here is T1 and T2. We're assuming here is the increment between this period of time. Here's the increment between this period of time. We're assuming they're independent. For any and the last thing is the increment actually stationary. What that means? That means start from today. You talk about what happened to one day. So T2 minus T1. This is tomorrow compared to today. And also, if you do the same thing next week, even after a couple of days, a week, but the increment will follow the same type of distribution.
This is between the NCTS 5A and NCTS.
That's a good question. Yeah, I'm not quite sure. So let's say T2 plus also T. T and T2 minus T. So any so here is the time shift. One thing you can think about, right? So whenever you talk about, as long as the time difference is fixed, so the time distribution will be identical. It's independent where you start. It just saying like, what do you think about what happens to tomorrow and say today and tomorrow? As long as the time duration is similar or same, and this should follow the same distribution. So any Poisson process will follow or will have satisfied the following 4 conditions. You guys with me, right? That's what we did last time. Then here is a few comments. And what's the expected value of any fixed T? This is the Poisson random variable. And last time we talked about the mean and the variance of Poisson random variable is the same. Given factors, whatever this parameter. So T is first day, remember the 10 message, 2 days, 20 messages, 3 days, that will be 30 messages. So that's the mean. All right. And second thing, what's lambda? Lambda, you can think about this is the average number of average number of events that basically happening where any unit of time which has period 1. So that's what lambda means. And then if we know that, So the key, the second comment, the third comment is the waiting time. Let's say, let's define this. So that P5 defined to be the S, let's say inter-arrival time of the S arrival. What this means, start from the very beginning, that's time 0. This is time, like the text message. This is the time you receive your first time text message. And sorry, I didn't put this right. I should put this right here. This is T1. This is T2. This is time and start from the first one after you receive the first message. So that's why it's called interval, intermediate time. From the time you receive the first one, here you receive another one. Now you keep going. And the key for Poisson process, this is something super important, and it follows exponential distribution. Last time we defined this with parameter lambda. And also, they are IID. Do we still remember what IID means? Identically, independent, distributed. Very good. Yeah. So then NT basically is what? Poisson process at any time is a supermom of N such that N's arrival time is less than T. That's basically how they're related. And now by strong law of large number, which we discussed last time, now we know this is what? If you think about interval time, this will be simple mean, the average. We know by strong law of large number, this will converge to what? The true mean. What's the true mean? The true mean for exponential distribution is 1 over lambda. And roughly think about what? Suppose you receive on average 10 messages a day. And that means on average, how long you will receive one message? 1 over 10, right? So that's what this means. And by strong law of large number, we know this convergence to the population mean with probability 1, almost surely. All right. So, or another way you can think about, if by time t you receive no message, it's basically what? Is the first waiting time is bigger than t, that will be E negative t for any t. All right, so now once we know this, we will know how to simulate any Poisson process. What's the key? The key is for Poisson process, of course, which satisfy those 4 beautiful properties. And the key is the inter-arrival, intermediate time is what? Is exponentially distributed. So that's the key. Once we know how to simulate any what? Exponential distribution, the waiting time, then we can do this. So I'm going to send you a code by the end of the first section of today's class. Maybe we can run those together in the second section. Do you guys like that? All right. So now let me show you, maybe I'll show you the example. Now here. I'll show you example in the second part. It's basically talk about in a small community, suppose very small community, small city, small village. And so average number of infected people each day, let's say fixed. Now we're trying to predict what happened to this infection. We're going to use Poisson process to simulate that, to model that, and we will try that together. I think I'll postpone that example, to discuss that example in the second section. Now I would like to refresh you what's a Poisson process, what's the key feature. The key feature is inter-arrival time, just like, and he talked about the car accident, right? Number of car accidents, say, and each certain location at certain day. You with me? So then this is saying the inter-arrival time between the two subsequent car accidents follow what? Exponential distribution. So that's the key. When we use this key to simulate Poisson process, then we will see what happened to that example. Okay? All right. So let's see where we are. Can I click this part? Finally, see, before we call chapter 0 for the second part, the custom process, it's kind of hopefully give you guys the big picture of the foundation we needed, which we summarized last class. And start from today, we're going to have a quick introduction about stochastic process. And stochastic process, and last time we defined this, recall a stochastic process that's complex. Indexed by capital T is what? It's a family of random variables. Indexed by capital T. That's it. And so in particular, for each fixed T, we know this one is what? Is a random variable defined on what? A probability space. This is sample space. This is a sigma algebra. We talk about this P is a probability map. That's second thing. And T usually, not always, okay, usually represent time. Think about in this case, you're trying to count what? Number of infected or number of deaths happen per day, right? Or like over time. So you basically clicking this and T will be, your index T will be at that time point, what happened to your infection situation, okay? All right. Then, of course, this process, the stochastic process, telling us what? How the state, this is at time T, what happened? Evolve over time. I should say, not always is time, over time. If you think by index is, let's say over T, over time is too restricted. And then, of course, if the index set, this is countable set, then what happened? Then this process, you have either finite many or countable many of these events. So this is called discrete time stochastic process. Of course, if this is uncountable, and this is continuous time stochastic process. And say, for instance, if T is what? If T is R2, this calls the classic field. And similarly, you can consider this is what happened to the index. Similarly, you can consider the state space. Say, if there are only like car accident, that only can be integer value. You cannot have like 2.3 number of car accident. What does that mean, right? So when your state space, let me put a quick comment over there. Likewise, the process could take value which could be what? Which could be integers or real numbers. Then we will have what? And then we call the corresponding process. The corresponding process. To be discrete state space. Call this one to have discrete state space or continuous state space. I think about if we're trying to, so you're trying to get a new laptop. And of course, price is number one and brand is another one, right? And then the other concern, it depends on how often you will use your computer, how intensively. You probably will think about what's the battery life, right? And what's the memory storage, all that kind of thing. But in terms of, let's say, a battery life, that's what? And the state space is not going to be 1, 2, 3, 4. It's what? It's continuous, right? Start from 0. Of course, if you get a battery that's 0, that from beginning, it's very unlikely, right? And to be any positive number. So that's a continuous state space. But your text message, car accident, say any of like a number of people visit Hsinchu like today, that's all what? State space. Can only take discrete values, okay? All right. So of course the Poisson process, for instance, what happened to Poisson process? Poisson process is what? It's discrete in, say for instance, Poisson process is what? Is what? Is continue in time, discrete in state space. Is a standard example which is continuous in time and discrete in state space. Because this count number of certain events that happen, that's discrete in state space. Like if you have a process, each of them follow a normal distribution path. And like think about diffusion case. So here I have a very nice glass of water. I put a drop of ink. What happened? You will see it will diffuse, right? If you look at how the process diffuse, start from very beginning, it's really focused on where I drop the ink. Then it start from that point exactly as Hongdao said, and it's going to diffuse. So this will be basically can be captured by something called Brownian motion. But the point you can think about the distribution in the very beginning is like this. The very peak, very highly focused, but not much distribution otherwise. However, as time goes, it become flat bell-shaped curve, right? So that for that case, that's continuous in time. That's something called Wiener process or Poisson process, and continuous in state space. You guys with me? So Poisson process, not Poisson process, the Brownian motion or Wiener process, another name for Brownian motion, that's Brownian motion, is what? It's continuous in time, continuous in state space. You guys with me, right? Are we together on the same page? All right. So now we can let's get a quick review about the development of stochastic process. This is totally unlike the stochastic situation. You know, we have so many elegant, beautiful results, fundamental results, a clear picture about deterministic case. However, for stochastic case, first of all, as you will see, the development is not until pretty lately that happened. And second thing is many things is still under construction. Just like every time I came to Tsinghua University, there must be some buildings still under new instruction, right? Still under instruction. Many things are still unclear, unknown. So that leave us, you guys, a room to make efforts, meaning many things are unclear. You guys all know the deterministic case. You have beautiful dynamical system result and bifurcation theory, right? And but for stochastic case, how you going to define and essentially what do you mean by something like a bifurcation? It's not quite clear. You guys know deterministic case, what bifurcation means, right? So say for instance, as your parameter change, there is a fundamental quantitative change in terms of solution, the behavior. But for stochastic case, how are you going to do something similar? Okay, all right, many questions. So the early roots, of course, coming from probabilities, okay? So this is 18th to 1900. So there are a couple people. One is the Legendre and Gauss. And the other one is Bachelier. And here is a Pearson. So what the Legendre and Gauss is, they basically introduce, I think Legendre probably may talk about model fitting later some point, right? So one popular approach to do parameter estimation on model fitting is something called least square. So Legendre and Gauss actually introduced the idea of least square. And then this guy, he did what? This is the first, let's put it this way, first mathematical model for Brownian motion. Brownian motion. We all know Brownian motion, right? Yeah. And Pearson, what Pearson did is, this is the early development for what? Early development for random walk. You know, the interesting for this guy, Bachelier, and he actually, and this work, and talk about Brownian motion. This is the first mathematical modeling, and he introduced in his PhD thesis. Do you guys know who his PhD advisor? Henry Poincaré. Of course, one of the greatest mathematicians in the world over this time. But you know, when he did his PhD defense, he barely get a passing degree. Yeah. And Poincaré comment on his thesis. He said this thesis, this basically is for financial, coming from a financial application, mathematical finance. And it's really lack of what? Mathematical theory of rigorous foundation. But he gave him a pass. And so that's what will happen. That's about 1900, beginning of 1900. So even he did this, and Poincaré, of course, Henry doesn't really like his work, and nobody really pay attention. And he did a couple of remarkable things in his PhD thesis. One is the Brownian motion. The other thing, actually, he expects something called Wiener process. And the other thing is, when it's come to 1970s, a black show. 听过 black show 吗？就是这个是 stock price 非常有名的那个 black show 也因为这个拿了 Nobel Prize。Anyhow， 是因为他们也用了，就是事实上是他的类似的 idea， 但是 nobody know his work until seven decades， 就70年之后才会知道他的这个工作，没有得到足够的认识，很可惜。对 ，Anyhow， 这是 early root。然后是 ，and 这个是就是 physical， 就是 first rigorous development that's from physics point of view of ground motion， 是谁做的呢？是 Albert Einstein 和 separately, they work independently.这个 basically 就是 foundational 的基石，但是它是从物理的 physics point of view， 他们来定义这个。然后真正的 rigorous construction， 是 Wiener。这是为什么那个 Brownian motion have another name called Wiener process？ 你看这 Wiener 更有意思了。Wiener， 他是has a lot of interest, but he said at some point he commented, I can become a mathematician most or largely because my father didn't allow me to do anything else. And then he became a very famous mathematician, one of the greatest contributions, and his work is Brownian motion, because he really gave the mathematical, theoretical or definition of the whole thing, rigorous definition. And next one, I hope we will have time to talk about this as well. Kolmogorov equation. This is the modern measure theory base of stochastic process. Then later, of course, is a Markov process. Markov process. Is developed by Markov. And here there are many things. He developed a champion Kolmogorov equation, like the things we're going to discuss in the second, discrete time Markov chain, continuous time Markov chain or Markov process. And now, more recently, he developed a modern theory for martingale and equal calculus. Of course, This is done by Duke, this is done by Ito. I hope we have some time to talk about those. This is 1940 to 1960s. Here is done by Duke, this is done by Ito. You guys heard about Ito, Japanese mathematician. You must have heard something called Ito's formula, right? And and the time he's doing all this work is Second World War. And I think he published a couple papers that contain the foundational piece for stochastic calculus and like Ito formula, Ito formula, Ito integral. Ito formula is like what? You guys all know for classical calculus, we do chain rule, right? If f is a function of u, but f is a function of g, but g is a function of x. When we differentiate, we do chain rule. But Ito's formula is kind of like different way we do this. And then, of course, stochastic calculus in his papers. And of course, nobody cared at the time he did this until more recently. This is the application of stochastic process, which is banned start from 60s and more dramatic becomes 70s and until now. For 70s, so there is a Black-Scholes model. Black-Scholes, not Black-Scholes, Scholes actually got a Nobel Prize. Even you see this model is named after two people. They apply Ito's calculus to study what? The stock price. 不太会翻译 stock price 叫就是对因选商品价钱，谢谢郑老师。对 stock price, but the point is, you see this key foundational work and consists of at least two names, right? But Black actually didn't get Nobel Prize, and Scholes got it. You must wonder what happened, because they gave this work and Nobel Prize, and Black was died 2 years ago, very unfortunate. Anyhow, so I hope we will have time and to talk about most of this and the stuff. Now, by far, I hope you have a general idea about the stochastic process. The point is there are too many unknowns, and in terms of the theory of stochastic process, meaning we have a lot of room we can put into it. Like right now, if you look into paper articles or like book journals, book chapters. And so most things related to stochastic process, you saw a lot of simulation, right? But the punchline or the key is what? The theory is not fully developed. There are many things uncertain, unknown. Okay, all right. So now I think we're ready to talk about this.
So,
哎，林老师你讲。
time discrete and continuous stochastic field 稍微解释一下。
没有，它就是这是他研究的是说，它这个 index 其实是双重 index、double index， 所以你可以想成是在整个平面这个 field 上的。这个应用很多，尤其研究 spatial statistic， 就说你有很多比如说你看 climate data。 它不是 change over different 有 heterogeneity over the 比如说 entire Taiwan， 你看它的那个就 climate data， 它会随着时间每个地方都会在变，对。然后如果你把它 layout snap fix 时间 over 这个 entire space 的时候，你就可以想成这是一个 field 在一点的取值，就是高维的嘛，就是一维的 index 不够了。当然，你需要更多的 information more involved 的时候，你就会有高维的 index， 就看你怎么去想这个问题。对，好。Next question. Discrete time Markov chain. Of course. So now the index will be at most countable. So how we define this? And now, because it's a chain, this is discrete in time, discrete in state space. Right. So how we define this? A stochastic process. Oh, 我这样写出来，我还没定义这个。哦，定义了哦，我们可能 we introduced this notation last time. That really depends on how you use it. If you only have finite state, you probably won't start from 0, t equals to 0. You probably, if you have only 3 states, like here the weather could be what? Rainy, cloudy, and sunny. You only have, say, for instance, a couple of states. You probably would say first state and rainy is 1 and 2, cloudy is 2, and sunny is 3. You see what I'm saying? It's how you index. But how you index is in terms of time, it could be at most countable. So that's why we do integer. But sometime for convention, they may start at time equal to 0. So that's why they also include positive or non-negative integer, including 0. You guys with me? That's just the index. It's called a discrete time Markov chain. We will say DTMC. If for each n in the index, this one has to be a discrete random variable. This is saying discrete in state space. And second thing, this is saying each fixed time you have discrete random variables. So you are a chain. Then we got to see what Markov means. Sorry. Let me change a notation. I think that may look better. If I use n, you kind of feel like this is discrete, right? Yeah, let's use that. I think that's a better notation. So the process satisfy Markov. Property. What this means. So here's what happened to the nth step size. Say equal to something. I got to have a name. And given whatever happened in the past. Let's write one more. And last time we defined what this bar means. This is conditional probability. It's saying at n+1 state, say your future, here is your state. And given what happened to the past, yeah. But if this is Markovian, and this will be only depends on the present. Sorry, IN. Oh, did I put the index right? What I'm saying is, here is everything happened in the past plus present. This is, you're trying to predict what's the probability of something happen in the future. But if it's a Markovian or it's Markov, what that means and what happened in the future only depends on what happened to the present, is independent of the history. So that's Markovian. It's kind of, this guy is what? Memory loss. So doesn't have memory. So past is independent or has no impact to the future. Of course, this is a very strong property, but it simplifies things a lot. All right. So let's see a toy example. This is a very simple SAS epidemic. So very simple epidemic model. So suppose each, let xn to be what? At nth time unit, you can think about day n, okay? So it could be either 0, 1. 1 means what? The individual you care about, individual, is susceptible. Say at time n. And 1 is basically saying this one is infected at this time point. So this fixed n, this is what last time we talked about. This is the Bernoulli random variable, a binary Bernoulli random variable. Clearly, as your running start from day 0, day 1, day 2, etc., you will get what? It's a discrete time Markov chain. First of all, it's already discrete in time, in space. And second thing, this satisfies the Markovian property. Right? All right. So let's see another example. You know, for probability, where probability development actually start, it starts from what? Gaming and gambling. Gaming and gambling, is that's where probability start. 概率论是从博弈论开始的，不是博弈论，就是 game theory，不是 game theory，sorry， 是从 gambling 开始的。Gambler 是论。So what's this? Suppose a guy, a gambler, 一个赌徒啊 he wants $N, okay, it can be anything. Say $100,000, whatever, that's it, okay? But he only has $I. Of course, I is between 1 and -1. And now he plays games. That allow him to win. I gave him chance P of winning $1. And chance Q of losing $1. That's super simple. So every time he played, so he will either gain $1. What's the likelihood? Probability P. Or otherwise he will lose $1. What's the probability Q? So what's the relationship between P and Q? Very good. Must be 1, right? So here's the game. And when he basically, he wants so much money, $10. So when his fortune achieved whatever is either $10, he win, or $0, he totally lose, and the game over. He stops. And the question is super simple. The question is asked, what's the likelihood? What's the probability? He wins. He wins means he got $10. Is the question clear? This is something known as gambler's room problem. So far, so good? Okay. All right, let's do this. First of all, so let's say Xn be what? The amount of money, the amount of dollars he has in the nth game. So we all know when he start with $I. Next time what can happen, there are two possibilities. Either he gain 1, become I plus 1, or he lose 1, will become I minus 1, right? Okay. All right, so, clearly Xn is a discrete time Markov chain. Discrete time, no problem, right? Is counting each game. And Markov chain is what every time only two things can happen. So it's going to take from, it depends on what your current value is, either +1 or -1, right? So discrete in state space. And Markov win is because this assumption. This is saying this is not true. If you keep losing, that will affect how you think, how you're going to try later, right? This is assuming, so this guy is, every time he plays just like a new. You see what I'm saying? I'm saying if I keep winning or keep losing, that will change how I'm going to do this. But right now they're assuming every trial, every game, they are, each of all those games, all the trial, they are independent. So what happens next only depends on what happened to the gambler at the current time step. So that's Markov win. So this is a DTMC, discrete time Markov chain. All right, so now let's say we want to know what's the probability he win. What that means? That means he start with $I. He's going to win at any, if he win, he must have $N, right? That's his goal. So N can be, of course, N cannot be. Let's say N is anything because we can do what? We can do like here. Start for $I, and at the current time, the probability you win is 0, right? And next time, if I is far below N, of course, the less the N, the likelihood is smaller. But this basically is what? Which is what? Which defines the success probability. Or winning probability. Because this is taking care of all the possible situations, right? You start with what you have, $I, and now this is counting what happened next for all the possible cases. But once you get N dollars, you're out of the game, right? So that's the probability. But the point is how to do this. I want to show you this. First of all, it's super simple. Also, it's a famous or canonical example of this. And third of all, I want to show you a method. So let's do this. What do we know? Of course, this I is between. Now I extend this I, okay, to including the boundary case. What he has really is start from one, at as small as $1, at most is N minus $1. But anyhow. So if I start with $0, you will never be able to win because you're out of the game, right? So this is 0. If you start with total amount of N dollars, also you're out of the game because you win already. So this is what? If you start with N dollars, so you automatically win. The probability you win is 1, right? So that's 2 trivial boundary condition. Now, here is the key. Let's do this. Oh, let's, maybe I write something I start with $I. And this guy can either win or lose $1 in one game. Only 2 possibilities. So I start with 1 play. Now I know if he gain, what's the probability he gaining is P. And then, however, if he win, the probability of success will be alpha I plus 1. If he win next game, you have more chance to win the final fortune. But there also another probability or likelihood for next game. He can lose. If he lose, now the probability is success because he's going to have $1 less. So that'll be I minus 1, right? Now the probability of success will be alpha I minus 1. This is called one-step method. It has been used a lot for doesn't have to be discrete time, continuous time, and it's the stochastic process. Meaning I have no idea what I'm trying to study, but what I'm doing. You can do 2 things, guys. You can either move forward, I'm moving forward right now, 1 step to see what happened, or sometimes maybe you can move backward 1 step to see what happened. Okay, so now, can we solve this? I think everyone can do this. We know this, and we know this recursive formula. Can we solve this? Of course, right? Look, this, remember, E plus Q is what? It's 1, right? So this is recursive formula. Everyone know how to solve this, right? So if you solve this, I bet you know how to solve this. The telescope, this is geometric series, right? And initially we end up to solve this. Alpha is this. Q I. P. O. Q over P. I to once and here is the probability wins. The key I want to show you is this something called one-step method. Looks, idea is pretty simple. You just either go forward one step, check what happened. That's how they derive something called master equation, something called Kolmogorov equation, many things. That's the idea. Or you go backward one step, and you also can try something similar. Of course, now for this one, this is super simple, like classical problem from probability. Now you can see if the chance, unless this one is very skilled, this gambler, and typically that means a fair game. I don't know. If you go to a casino, you're going to play a fair game because highly likely you're going to lose, right? Yeah. Anyhow, suppose P equal to Q equal to 1/2. What happened? You can see. Then, if equally likely you're going to gain and lose every time you play, it will be I over what? What's the denominator? How many copy? The top is I copy, right? Bottom and -1. So you would know that's if equally likely, that's the chance, right? All right. Let me clean this. So now, when you have a DTMC, how are you going to capture things happening over or steps? Just like gene mutation, like we're saying, most of us going to have, say, think about you have parents, and parents now have you, and you probably find your partner, and now you two get together, have next generation, right? Or you think about genetic, like proliferation, like cell growth, or like mutation, and things are going to evolve. How to capture this? So we're going to introduce a notation called transition probability. That's called one-step transition probability. Of a DTMC, discrete time Markov chain. All right, another way. This is another way, typically we'll write. So now, is the probability is the following. Probability. So count PJI. Usually we call it IJ. There's a reason. I'll show you in a second. You can do the other way, IJ, as well, but there's a cost. What's this? This is saying at time step n, I'm at location I. Now I move in one step, I move to location J. Oh, this called state I, is this state J. Just say, now here is cloudy. What's the likelihood tomorrow going to be raining? It's a one-step probability. And I is, say, cloudy is 1 and J is raining, say, state 2. Okay. All right. And N is saying you start from where? It depends on what time you start. And then this could depend on what happened now and what day. And all you think about this could depend on what's the season. All right, so, and one quick remark. All possible J, what's this? J is overrunning over all the possibilities. What's this? This is saying, think about the weather case. As right now, is this cloudy or sunny? You guys tell me. Is this cloudy or sunny right now? Sunny, okay, I like that. Yeah, and suppose right now it's sunny, and now that's I. And tomorrow could have how many possibilities? Oh yeah. Could be sunny again, could be cloudy, could be rainy, right? But when you run of all the possibility in terms of J, what must be happening? You add up all the possible outcome. So the probability, sum of this probability must be excellent, must be 1, right? So what this means, if you think about this PJI is this is a one-step thing, right? One-step transition matrix. And it doesn't have to be finite, depends on how many state space you have. Like a weather case, that's 3 by 3. In general, is what? It's count by many, like, right, sorry, count by many, N0 by N0. But the point is, this matrix has column sum is what? Is 1. So when you have transition matrix, indeed, that will determine or be able to capture everything about this DTMC. Remember, last time we talked about, if you have a random variable, you have at least 3 different ways, actually, if there are more, 3 different ways you can calculate them. Because random variable, every time you're doing this, you have unpredictable outcome. If you run the trial, anything can happen. However, how we're going to capture this random variable or random distribution, we can use something deterministic, which could be either probability density or mass function, probability density function, or could be cumulative distribution function, or could be moment generation function. There are even characteristics. So what I'm saying, we have deterministic way to capture the stochasticity. Similar. If you have DTMC, if you know the transition, I haven't defined, this is transition probability. And I put it together with transition matrix. Of course, a DTMC, square time Markov chain, is said to be, it's important, homogeneous DTMC. If what? If the one-step transition probability is independent of N. This is saying, suppose N is today, this is tomorrow, but N could be 100 times day back. That will be 99 day back, okay? And if this is independent of N is, every time you're doing this, it's like the same process. You're repeating the same process. So that's homogeneous. Then this is, remember, we talk about Poisson process. The last property is something called stationary increment. This is kind of analog to that. So it's independent which N you are. As long as this is a one-step thing, you always have this. It's independent of which step you start. All right, so here we have the DTMC. With one-step transition probability. Transition probability. PJI. Oh, not all the positive IJ. So then I should say, in this important. Homogeneous discrete time Markov chain. In this case, the one-step transition probability is independent n when you start. So I can simply call PJI. Then the transition matrix is defined to be matrix. D is defined to be what? PJI. Oh, I'll write it down. P00. You guys got the idea, right? It's the one-step transition. But right now, you see, I remove this one because it could depend on when this start. If it's time homogeneous, that will have stationary increment. In that case, and you have homogeneous discrete time Markov chain. So this will be independent which step you start, will be just PJI. Then we put all this PJI together, we got the one-step transition matrix. So this will be a characterization for a homogeneous DTMC. For DTMC, if it's not homogeneous, why we're doing this? If it's not homogeneous, you have to collect this every step because every step could be different. Okay, I think we can take 15. 还没开始，还有几分钟，是吧？你们这样听得懂吗？可以吗？对，现在就是有点难过的是说，可能就是每次都是听一部分，然后可能有点连不上。如果可以的话，也许可以问问其他有同学能比较有时间听到全部，然后也许你就会看到 whole picture。对，今天我们现在讲的是，我们又开始哦，你们现在可以继续自由活动，叫 discrete time Markov chain。这个就是首先你要知道什么是Markov chain 或者什么是 Markov property。对 ，Markov property 就是说你现在如果考虑接下来要发生什么，它事实上又 depends on 你今天发生什么，你当下发生什么和之前发生什么的 everything， 对吧？是给定这些我才能决定接下来发生什么。就比如说 stock price， 我觉得成绩也不是太，你们的成绩也不是太依赖于 past。Anyway， 就是说接下来发生的跟之前你们这样说好了，你们现在都非常 proud of yourself。你看你 either 是那个清华或者是交大的就是学生，对不对？没错。可是你能走到，因为台清交可能是台湾最棒的几所大学之一嘛，那你能走到这一步，就取决你小时候是怎么样子的，对不对？幼稚园是怎么样的？小学在哪儿上的？初中在哪？你们叫国中在哪儿上的？高中又在哪儿上的？然后你经历了，就是跟谁去学了什么东西？你有什么样的 experience？ 然后你又做了什么活动？又参加了什么 event？ 每个 step matter 才 accumulate 今天这是成就你 beautiful 的你。我说的意思 ，in general what happened to you in the future 是 depends on entire history 的。可是 Markoven 说白了是什么 ？What happened to you to the future only depends on what you are doing today. In some sense 也是对的，就是说你要决定你未来是不是能成为一个，我不知道你们可能成为一个数学家，或者是跟数学有用的相对工作，你就会想，我每天做的这个东西，就是当下这个东西都会 affect。他说的意思，那现在这个 future 不 depends on entire history，只 depends on current time step， 你就活在当下就对了，就这意思。比较乐观哈 ，Markov 比较乐观，这是 Markov。Discrete time 就简单了，说当你 running time index 的时候，我不是看所有的 time， 比如说我只看第一天、第二天、第三天，或者第1个小时、第2个小时、第3个小时，或第1年、第2年、第3年，是 discrete time。就这样，我们刚才就讨论的这个，然后我们现在想 capture 它，叫 something 叫 transition matrix， 这个时候必须是 homogeneous stochastic process 才行。那你就看什么是，那你想就是 Markov 不依赖 pass， 这都没了，对吧？这个是 n 次 step 它的状态，这是 n 加1 step 它的状态，这是 one step transition， 因为这个不 matter， 对吧？那这个 n step transition in general 它是 depends on which n 的。可是如果当这个 transition probably independent 那个 which step of n 的话，它就叫 homogeneous。如果是 homogeneous 的话，因为如果你做这个的话，每一个 step 你都有对应的 matrix， 第2个 step 有个 matrix， 第3个 step 你要 keep track of all the transition matrix too complicated， 对吧？那一个简单的简化就是说这个不依赖于 n， 那这个时候 P1、P2、P3 都是 P， 就是这个意思。那清楚了吗？到现在，易翔是那位，光辉是老师，轩，凡是那位吗？入场自选为凡，博士。谢谢，谢谢李老师。李老师 ，NCTS 应该配你哦。没有，挺感谢你每次都这样帮，没有，不是，很感谢你。对对，想必现在比较忙。
他们现在就开始，对，那时候礼拜就开始，自白，哦，是教我就是这个，爱做料理，对啊，是。
我刚刚把 code Sorry, I just sent code to everyone. You may want to check your email in one minute, in a minute, to see if you receive it. 有收到吗？有哈。OK, thank you. 我们 shall we restart? 好，先把电脑关起来。
好像还没有收到。
不好意思，是线上的哪位同学或老师在讲话吗？
我陈冠维，冠维，
冠维，你没有收到吗？我有把你的 email 放进去。
还是要等，可能要等一下下。
哦，等一下，我看一下，我好像有把你的 email 放进去。你们都有收到吧？
有。
为什么冠伟没有？有啊，我有发给，哎，奇怪。
但是有比较少。限定。
冠伟又发一份给你，你要不要再试试看？
我确认一下。
好。And indeed, a quick method to check your transition matrix, of course, you need to check the general component. A quick check, you want to check if the column sum is what? Is one. 为什么是 one 呢？是，你看它这个是 summing over all the future possibilities. Start from I. That's all your possibility. You summing over all the possibility, of course, is one. What's acceptable? An individual is just acceptable. So we define to be zero. If it's infected, we define to be one. We already know. So the discrete time marker check. 那我们现在看一下，你做一个最简单的 transition 好了。Force in 0, 1， 全是 probability. The probability that a susceptible individual become infected in one step. 我们现在假定这是一个 SIS epidemic or one individual，你就可以假定是什么呢 ？You can think about 这是一个 one node on the graph，这个 node represent the infection state。然后如果这个 disease follow SIS epidemic，所以 each individual on the network 或者 on the graph，它 only have two possible state，either susceptible or infected。And P and D just be the transition probability. So this is saying an infected individual actually what? Recovered, but without immunity, so become susceptible again. So. Matrix. So let's see. Can anyone tell us in this super simplified case, what's the transition matrix or one-step transition matrix? 0 is S, 1 is I, and B is the probability from S to I, which will be 0 to 1. So how does matrix look like? You guys with me? This means what? This is the probability. Sorry, I erased everything. This is the transition probability from 0 to 1. 0 is susceptible, 1 is infected. So by the assumption, P10 will be 是 B 还是 D？ 再一次啊 ，P10是什么？我都不需要 one， 这是 n 加1，任何一个人都对。One step, given current situation 是 zero， 记得我们写的不是 I 接，是 JI， 然后你 transition to one， 对吧？所以这是 P10, which is what by definition, by assumption, BOD. This is the probability from susceptible to infected. So which is B. Excellent. So this is B, right? Likewise, this is the probability transition from infected to susceptible, which is, remember, we call this is I. I is where we start. J is where we go to, right? So this is D. That's it. So now we know this is B, this is D. Can anyone tell me what's the question part? I need one volunteer. I know many of you guys know. What's this? What's P00? 我们刚才讲了，如果 P 是 transition matrix， 它有什么特点？它的 column sum 是 one， 对吧？那如果这个是 B，column sum 是 one，this must be one minus B。如果这 column sum 是 one， 这是 D， 这一定是 one minus D。OK， 所以这是 one step transition， 这是 super simplified 的。What I focus is one point on the network。each individual 就那么几个 state， 你可以 SAR， 那你的话就是 0, 1, 2或者 1, 2, 3，that's up to you， 对吧？一样的 story。So far so good。等一下我们会做一个简单的 simulation， 关于这个 example SIS epidemic。对，这是 one step。刚刚我们说了，说这个 one step transition matrix can capture everything about this process。然后现在来了， 先这样讲哈。那我们先看一个 notation。我又不想看 one step，I want to know n step。我想做一个假定，我们就不用一直写 DTMC 了，好不好？可以吗？我就做个假定。Homogeneous discrete time Markov chain. Without any further statement, all the process we talk about by now is this. So now we talk about n-step transition probability. 这个 n is upstairs, okay? It's a superscript. 这怎么定义的呢？是说 when I start at I. After n step, I'm at J. This is not one step. This is n step transition probability. 这说今天是今天算晴天，然后明天我预测明天天气是 one step， 但是我预测一周以后的话，这个可能就是 seven step 或者 eight step， 就这意思，就是 n step transition。这个是零的时候，这是 n 的时候，这是 state I， 这是 state J。你想看 how likely this transition going to be happen？ 啊，现在就来了。All I have a homogeneous discrete time Markov chain. All I have is one-step transition matrix. 比如说这个 simple example 就是它。那我能预测所有的 future 吗？我刚才说了，我知道它就知道 everything。所以我现在的问题是说 n-step transition matrix。in N 这样的一个 matrix。Of course， 这是 one step。我现在问题来了，当然这个是什么 ？Zero step transition。我从 I step， 我如果是 zero，n 是 zero， 我从 I 开始到 j， 如果 I 不等于 j 是不可能的，对吧？我还没开始嘛，所以它是什么？只有 I 等于 I 的时候是 x0 equal to I， 我 go to x0 equal to j， 只有 I 和 j 是一样的时候我才做到，对不对？我从 zero 的时候，我 start with I， 我 stay at I， 我还没有做 transition， 所以这个是个什么？这 chronicle delta， 大家知道是什么意思对吧？这个是 one， 如果 I 等于 j，others 它是 zero， 对吧？换句话说，我知道 one step transition 就是 p，zero step 是 identity。我知道的是这个就是 p， 这个 zero step 就是 identity matrix， 这是个 identity matrix， 不一定是 n by n 的，可能是 n0 就是那个 natural number non-negative integers， 可能是无限维的。我现在的问题是说，我既然知道它了，我能不能有办法知道它 ？question 是这个。这是 n-step transition。这是 one-step transition。他们怎么 relate to each other? What's the relationship? 有没有 guess？ 大家明白我说的什么意思吗？大家有没有明白我说什么意思？我现在跳了 n 步 ，I jump n steps。我说了，如果你有个 homogeneous DTMC， 你只要知道它的 transition matrix 或者 one step transition matrix， 你就可以知道 everything。那我现在我想知道，我不想知道今天到明天发生什么天气，我想知道下礼拜发生什么，那我能不能一样做预测？ 那换句话说，如果我走 n 等于7的时候，这个和这个 p 有啥关系？这个怎么回答这个问题，我们就需要讲今天的这个 topic， 叫 Chapman Chromatography。Chapman。如果有同学做过 PDE 的话，一定知道这个人，对吧？很了不起的，我妈会不会是？哦，叫 C。这是什么？很简单。有没有任何 conjecture？ 比如说 P2 和 P 怎么 related？ 猜猜看。Free guys。我现在所有的 setup 都是这个，我没有写，是一个 homogeneous DTMC。有 conjecture 吗？你们一般做研究的时候都是怎么做的？你是不是先接触一下这个，然后看一些相关的文献，然后看看目前的 progress 在哪一步，你感兴趣的问题就出来了，然后看你感兴趣的问题是不是有人做过，没有的话你开始，然后当你做这个东西的时候，你会不会有一定的 conjecture 出来？Until you prove, you never know 是不是对的。那这里 P2 和 P 有什么 relationship？ 有没有？现在写成它也是可以的。这个看得懂吗？这什么意思呢？我是从 I 转到 J in n step. I'm going from state I to state J. 对 ，state I to state J in n step. What can we do? I can go from state I to any other state. I'm sorry, not any other. Any state in the domain in S step. Afterward, I have to go from K to J. What's this saying? 这是 I， 这是 J， 是 K。我先从 I go 到 K， 再从 K go 到 J， 对吧 ？K 是 any possibility， 不是 any state in the state space。如果没有的话，它就是 zero， 对不对？没有这个的话，它就是 zero。那这说明什么？这个 linear algebra 大家都知道了。你看这个 P1 等于 P， 那 P2 呢？是不是就这个？是不是就这个？所以它的 matrix form 更好看，更好理解。I think it might be easier. 我现在把这个 S 给它限定了，是大一点，小一点，看清楚了？这个清楚，这是 matrix notation。证明很简单，就是把直接这个带进来，证明它就对了。因为它 count 所有的 possibility， 对不对？这个证明是 straightforward 的。但是我现在更想让大家知道的是说，为什么我们知道了这个 P， 我就知道 everything 了。所以说这是说什么？ 子轩，你有问题？你说，
我在想那个 K，
哎，
这样子那个 P 前面那个 PJ 会不会 depend on
PJI，你说这个，
对，
这个 K 是 all the possible，我不是 S，我写错了，这是 K，这是 K，是 all the possible step，就是我现在就是说白了，我不知道明天你们想去哪里，也许明天你会回家，或者是明天你去 another place，我 just made it up，OK，Today you are in 新竹 ，Tomorrow you're going to 台北。但是 K 呢，你可以通过不同的方式，高铁、船，配船，Subway 是吧？火车有 train，然后又有 high speed train，然后可能还可以自己开车，是吧？那都是你所有的那个 K 嘛 possibility，这是你所有的方法从新竹到台北，就这个意思。那这是 matrix notation，如果看成这个 notation 的话。这个是说 S 是任何一个 step in between 嘛，对不对？你可以是一个 step、两个 step、三个 step。那现在你如果等它 take 它是 two 的话 ，S 是 one，你不就看到它了吗？对不对？那你如果再继续做迭代，这个是什么？是不是就是它？所以说我们 final answer to 这个 question 就是他们俩怎么 related。很简单，我 apply this n times，keep applying this n times。这样清楚吗？这就是你看，这叫 Chapman-Kolmogorov equation。这种 equation 它就是发展的早，我相信每位同学都可以 prove。如果你发现了这个规律，你也可以去 prove。很简单，就一行的 proof。
用强烈一样 DTMC，不是 DTMC 不会成立的。
对，不是 DTMC 可以做，就相当于你每个 one step 你都要 keep track。我们刚刚讲了。你不能是 P乘以 P， 对吧？你会是什么？你会第一个 step 是 P1， 第二 step P2， 就是 one step 是从哪儿开始的？就是你从你的 transition 你要 keep track， 从 P0 开始的 ，P1 开始的 ，P2 开始的 ，P3 开始的，每个都要 keep track 之前发生。你当然可以做，只是你的，因为这个可能是一个 infinite dimensional matrix， 对吧？你要继续这样做，一定 very expensive， 可以做。您懂我意思是吧？
大概没有抓得很准。
我说的是 remark， 这个是很好的范式。If the DTMC is not homogeneous, in 它不叫 heterogeneous, not homogeneous。那个这个时候，我现在是有 one step transition， 我们刚才是叫 P 上P1， 对吧？你下个要做的是说什么？你要记录这个，这是 n step， 我现在都要记录这个 one step 啊 ，sorry， 不是这个，写错了，你们别混了，这是 n step transition。我们刚才 introduce 一个 notation， 我们叫 one step transition for general DTMC 是 PJI。PJI 是这里的 n， 不是那上面的 n。它怎么定义的？它是从 i 转到 j， 但是从第 n 个 step 开始的。所以当你要做那个的时候，你这每个对应都有一个 matrix。我现在要避免 notation confuse， 我叫这个是 Qn 是等于 PJIn。这个不是 n step， 这是 one step transition start at n step。那你当你做这个的时候，这个 Q1 就是 P 嘛，对吧？那做这个的时候，它的 n step 你还可以做，你是 Q1 做一次 ，Q2 做一次 ，Q3 做一次 ，Q4 做一次。因为这是从 0 到 1的，这是从 1 到 2的，这是从 2 到 3， 这是从3到4的，它的区别就在这里。刚才我们就是偷了个懒，就是说所有的这种 one step 都是一样的，所以是 homogeneous 嘛。它是 homogeneous， 所以这个是 Q Q Q Q Q 或者 P P P P P 乘起来是 P 分子。讲清楚了。 那个如果是我们大家觉得11:50下课可以吗？还是你们要因为你们要走回听交大对吧？可以，就是我说如果11:50左右的话，我希望如果有同学可以11:20提醒我们开始那个 lab section， 好吧？然后，那为什么他有一个我让希望大家不要混？就是是 typical notation，但是我们不要混这个 p， 都是 probability。probability mass function of 这个 random variable for fixed n， 这个无非是说，因为这是一个什么 Markov chain， 它一定是 discrete random variable fixed， 这是 discrete， 就像 weather 你刚刚就那几种状态对吧？它是 discrete。那他说现在说是晴天 cloudy、sunny day、cloudy day， 还有什么 rainy day， 它的 distribution， 这是它的 probability distribution。可能这个是什么？比如说1/2是晴，然后是4/4是阴，然后1/4是雨，那加起来一定是1。所以这是它的一个 probability mass function， 这是 nth step distribution。那换句话说，我如果知道我现在的状况是 what's the likelihood， 我 have 这一种 weather， 我们能预测明天是什么样的天气？可以的。0的话就是 n+1次。哎，是这样想，或者是写不见。If this is your current step, what kind of distribution, whatever the things you care about， 这是 initial distribution。当你 multiply one step transition matrix， 你就会得到 distribution next step， 非常简单，对吧？这是为什么我 keep u, j and i， 否则的话你要把它变成 row vector， 然后把它转置了嘛？它的乘现在是左乘，否则是右乘，就是写成这样航向量，然后一样做了，只是差个转置。Anyway， 这个 one step transition for homogeneous DTMC， 我知道它的 transition matrix， 所以你给我当前的 distribution， 我一定可以预测接下来发生什么。所以如果我从 P0 或者是最开始的你initial状态，你告诉我你感兴趣东西的 distribution，I apply this n step， 我就可以知道 n 天以后，或者是 n 个 time unit what happened to the distribution， 就是只是 apply 这个 procedure n times。好，如果这个清楚，我们看一个 example， 这个 example 有点长，因为这是一个 paper 来的。这是它的 reference， 感兴趣的，这是从 ecology 来的，它的例子比较 simple。Edison 这个 paper 叫 Markov chain estimation。Avian seasonal quantity 这个是 ecological application。ecological application。So basically, in this paper, what Edison and his collaborator did is they use a simple. They propose. Let me put this way. They propose a simple Markov-chain model, simple DPMC， 而且还是 homogeneous。DPMC 够了，因为做1年嘛。加 homogeneous DPMC to study the reproductive activity of a single individual female bird, baby, in one season, in one breeding season. Where哦，这鸟是 Eastern Level middle mark。If you check out the original paper, they have beautiful picture of meadowlarks from Illinois, US. Anyway, so the ecologists, what they care about, 他想知道这个鸟 meadowlark 这个 Eastern meadowlark 它的productivity 就是说它怎么样去延续它的后代，在这个区域内。如果当它这个种群越来越少或者越来越多的时候 ，ecologists 就会比较 care， 他怕这个生态失衡，然后他去看这个。那现在任何一个 female meadowlark 这个鸟在 breeding season 它会有几个状态 ，has several activity. During the breeding season. One is actively nesting. What this means? So they lay eggs, and to maintain this egg, they lay eggs in the nest. And to maintain the nest until the young bird actually get out the egg and they flee. So they fly away. So that's step one. And second one, successfully fledged. So the bird, he gave birth, she gave birth to actually all successfully and grow up and fly away. This is day 2. It's just like a parents raise you now, you grow up. So then, of course, what can happen because of weather, all kinds of, you have enemy. And the nest before the bird even grow up and all get ruined. So they fail to do this. The last one is you quit breeding, you finish the season. And you know, in this paper, the remarkable thing, they use the data and from Illinois and to estimate the transition probability. So I'll just write it down. There is a long story. Transition matrix P, which is given by the following. Check those. This is the last row. This is the fourth state. They quit breeding. They finish everything. And now they quit breeding. Doesn't matter which one you are. And then they're going to wait another season and to restart breeding again. And in this case, state 4, this one. And you notice the last column consists of all the 0 entry except the last one. 这事实上是一个 absorbing state. Once they start quit breeding, you finish the season. And then the other thing you can check, the column sum all equal to 1. Like this one, this is saying what? This is 1, 2, 3. Now the Markov chain has only 4 state space, not like the general one we defined before, only 4 state space. And what this means? This, like this one, this is P2, 1. This is the probability. First of all, you actively and maintain the nest. Then 2 is what? Your egg become bird, they flee away. So what's the probability? It's about 37%. That's what they estimate. But of course, you have probability you fail to flee and because something happened, because you have enemy and ruin no, at least it's partial with the bird, so you're not successful. So that's the failure problem pretty high. So that's why they worry about this kind of mellow lark. Anyhow, so this is the transition matrix. What they know in the beginning, they know given what this means. This is saying initially I know half of the birds, they're going to make nested. They're going to be in this state, half of the bird. But since the breeding season already started, and the other half actually they even successfully breed the brook. Okay, that's the initial condition. So then they ask what happened to 1 season later. So how are we going to do it? What happened to the probability distribution 1 season later? This one is telling us, here's a P. And this one telling us, here's 1/2, here's 1/2. Oh, sorry, 0, not 0. X, what did I say? X0 equal to 1 or 2. Yes. In the first state and second state is 1/2, no other state. That's probability 0. So that's P. So you can do the simple algebra, just a linear algebra, and to check out. So here is the distribution after 1 breeding season. If you repeat this process, this is initially what happened. Half of the bird in state 1, half of the bird in state 2. And now no other distribution, but after 1 season, here's the distribution. Now you can repeat this, you will have what happened to the next season. So that's the idea. And since they care about the bird population, I think probably going down. And so they care about what happened and to see if they potentially can figure out something. But the remarkable thing is they use a simple DTMC to capture those. All right. So shall we see one more example? Oh, I can see graph. It's too specific, see diagram. Many situations could be like that. For instance, 如果是 disease situation, 你可以 think about 这是 three cities, three location. And I made up, okay, I made it up. Suppose here is Taipei, here is Hsinchu, and here's Tainan. Taipei, Hsinchu, Tainan. And now what's this talking about? This is saying not only the population, how the population going to move. And this is a 1/2 of the chance it's going to stay in Taipei. Now, 1/3 of the probability go to place 2, and the other third go to place 3, go to Hsinchu and Tainan. You guys with me, right? Now, here is Hsinchu, and 50% of people will stay, but the other half will potentially travel to place 3. And for place 3, they're not going to move out. Say, for this situation, they're going to stay. So that's maybe something could be helpful to not only study disease, many other things. So now here is the transition diagram. So what do we know? The initial distribution. X0 is probability X0 is equal to 1. So and the 2 is 1/2. I made it up again. I say initially half of all the population, half of the people is here, half of the people, the other half is here. That's the initial distribution. Okay, let's see what's the question. So now we want to find the following statistic or following quantity. Probability. One is, what's the probability? When I start, I'm in Taipei. But next time unit, say one day, I'm in Hsinchu, the next day over the weekend, I'm in Tainan. So what's the probability of this? Second, what's the probability mass function of X2? Meaning I want to know the distribution at second location. And last one is, what's the probability the first time to reach Tainan is equal to 2 time units, say 2 days. So here, T3 is defined to be the infimum time step you reach is the first time. It's the first passage time. First time to visit State 3. So here you see, we got 3 questions. It's a setup. Here's the DTMC. Once we know this also continues, homogeneous DTMC. So we know the transition matrix, one-step transition matrix. Can we write this together? 1 to 1 itself. So this is 1, 2, 3. 1 to 1 itself is 1/2. Now 1/3 you go to second place, 1/3 you go to third place. Then for 2, 1/2 you stay, and 1/2 you go to third place. And for last one, everyone stay. That's the transition matrix. So first, okay?
The row 上column 上的 first row first column
哦，那这个肯定是1/3了。Very good. See, that's good. Excellent. Exactly, you got my point. 现在说这个 column 上你一定得是什么？是1。Very good. 对，但是 1/3现在只有 1/3能留在台北。对 ，Very good. And once we have this. 所以说，我说当你做 DTMC 的时候，既然它是它的 characteristic， 你一定要 check 这个。只有刚才那个，我刚才那个有没有 check？ 我没有 check， 你们可以 check 一下 column sum 是不是 1？ 对，大概 check 一下。Anyway， 我知道这个，我知道它的那个，应该说原则上我知道它，我就可以 compute everything。那现在我来看怎么算这个 x0 equals 1。x1 equal to 2, x2 equal to 3。这是说什么 ？Initially 我在台北，然后我 go to state 2， 然后下个 step 我 go to 2天以后我 go to 台南，比如说这个意思。那我怎么算？这个是个 Markov chain， 对不对？所以你要做到这件事情，首先第一步你要在哪儿？你要做到这件事，第一步你要在哪儿？第一天的时候，你一定在 first day， 对不对？然后从这儿到这儿，这个还不 matter。从这儿到这儿是说 x1 second day，sorry， time 0， 这是 time step 1， one step 你要 go to 2， 你必须 given what x0 equal to 1， 对吧？就是说。Given 前一天我在台北 ，What's the likelihood I'm in 新竹？然后再 given， 因为我用了 Markov property， 否则是不对的。Given 前一天我在新竹 ，What's the probability？ 我在接下来的一天我在台南。为什么可以这样做呢？我现在想 compute 的是说第一天这样。第0天这样，第1天这样，第2天这样，发生这样的事情，我要先做的话，我第一要先确保第0天我是这样子的，这是我的initial状态。然后是说 ，given 第0天是这样，我要看接下来第1天我去哪。这个其实要看所有的 history， 但是我不需要，因为它是 Markov property， 我就看之前一天我在新竹，接下来我是要多 likely I'm going to 台南，这样清楚吗？就是它跟现实版的全部要求的事实上只差后面的那一项，但是因为它是 Markov， 它只依赖于之前的那一天你在哪里，这样可以。好，那这个是多少？就是最开始我 stay in 台北的概率是多少？你应该知道 somewhere 是这个是吧？是 1/2。啊，这个是什么？这是不是 one step transition？ 是从哪儿到哪儿的？从哪儿到哪儿？从 1到 2的，对吧？从台北到新竹，这个呢是 one step transition， 从新竹到台南，对不对？没错吧？然后我就在这个 matrix， 这是 Pij， 对不对？我来找。Where is 这个是 2？ 哎，我有没有写对？我也写对。1 2 1 2 1 2 2，right here， 是这个对吧？这是 1/3。 然后是这个，所以你可以算一下这个概率。换句话说，给你 transition matrix，你可以 compute anything related to your multiple chain。然后我们来看一下，这是第一个问题。第二个问题是什么？是 what's the probability distribution of second location？不是 ，what's the probability distribution of your process over 2 days？那这个简单。我们要看的是从 zero day 开始，你要 apply 这个 transition matrix twice， 对不对？然后你就看到 two day distribution。如果你把这 plug in 的话，我就不做了，就是三个。所以算这个 distribution， 你就知道，比如说种群呢。infection 呢，它的分布 after 2 days， 无非就是那个 apply p twice， 对吧？现在最后一个问题是什么？第三个是 What's the first time you visit 台南 the third place in 2 time you say 2 days exactly 2 days， 这怎么弄？这个怎么弄？开始了。然后我快点讲，那这个是什么呢？谢谢。我最开始 start 的时候 ，how many possibility I can start with? I can only be either the first location or second location. That's the only choice， 对吧 ？If I start with the first location， 然后 what I I go to start from the first location in 2 days. In 2 days, I go to location 3, 台南 right? 所以 what can happen in between? What happened to X1? Come on， 我现在是刚开始的时候我在台北，2天以后我在台南。我现在想问中间的这个 what can happen in between？ 然后你看 graph 吗？这是 zero， 这是 sorry， 这是 one， 这是 three。你可以什么？你可以 stay at one， 对吧？然后 go to three。你还可以什么？你还可以什么？然后 go to three。你可以 go to second place， 然后 go to three。还有什么？还有 initially 我可以 start with 什么 two， 对吧？因为 initially you have 50% chance you're going to stay in location 1和 location 2。你要 start at 2， 然后你要最后 x2 equal to 3怎么办呢？你可以什么？你可以 x1 stay at 2， 你还可以什么？这个地方。只能 stay at 2， 还可以去 1，x2 不能去 1， 没有 ，x2 不能去 1， 因为没有那个 direction。然后每个这个的 probability 都跟第一个类似，你可以去算，跟这个一样，你去算。然后最后的结果，我把最后的结果写在这里，是大概是26.39%。So that's the probability in 2 days you're going to visit the third location given here's the initial situation. 换句话说，你可以算 everything you want if you know the transition matrix. I think I'm going to stop here. Let me try this screen. Come on. Choose code.我现在想问，这个在座同学都用过MATLAB 吧？ 都会吧哈，对，知道怎么 run。线上的同学应该可以看得到。哎，为什么？
可以。
我接上了，等一下，这个 magic button 没有使。
这比您声音
我做早了，我已经做了这个 step。count 可以了哈。我们现在就把它打开。为什么什么都看不见了？对，你们现在可以看到我的这个应该你们大家都有嘛，叫 example underscore Poisson dot m。你们可以在 MATLAB 把它打开吗？然后我们现在来看一下，这个前面你们都知道是吧？我只是 clear setup，clear all，close all 是 close all the figure。如果你有，只是给它一个清洁的环境了。然后现在这个 lambda 是什么呢？这个 example 我没有写下来，是说有一个小的 community。然后我说 average number infection per day 是现在有2个人 infected per day。我想知道7天以后发生什么，1个礼拜以后发生什么，所以我 run 了 t max 是7。然后 initial 的时间当然是 t 等于0了。然后这既然是 simulated Poisson process， 我们刚才最 beginning class 我们 review 了 Poisson process 它的 key feature 是什么？对，是它的，你看 Poisson process 它的是 inter-arrival time 是什么？是 exponentially distributed。对，这就是它的 key feature。我说 inter-arrival 是说是从刚开始到第一个 first occurrence first event， 就相当于 first infection， 这个叫 T1。然后从 first infection 开始，再看下一个 infection，second infection， 这个中间的时间叫 T2， 然后就 keep doing 这个。所有的这个 inter-arrival 或者 intermediate time， 它都是 waiting time 都是 exponentially distributed， 这是 Poisson process， 而且是 independent。刚才我们还用了什么 law of large， 是 strong law of large number。因为 average waiting time 就趋于 exponential process 的 mean， 它的 mean 就是什么？是 1 over lambda。对，还记得对吧？这我们早上 review 的。好，那现在我就是要 generate 这个 inter-arrival time， 一直到 maximal amount。然后这个是什么？这个大家见过吗？这个就是无非我想 generate 一个 random variable，R&D 是个 random variable，which has exponential distribution。然后它的这个 lambda， 这个 MATLAB 的 built-in 的 lambda 和我们正好是 reciprocal， 所以我把它取成 1 over inverse。它定义只是它那个 PDF 写的跟我们不一样。好，然后这个 t 刚开始 t 是0，然后所以这个 capital D 就是第一次的，如果你第一次 run 就是 first arrival time。相当于是 the time to the first infected case， 然后你就 keep running 这个，你每次找到这个时间，你就把它记下来，然后你就会有一个 time series， 就 record the time for first infection, second infection， 然后 keep going， 对吧？好，然后我现在这个无非就是把它画出来，这是 time recorder， 是所有的 time， 你不需要 sort。因为 sort 只是从小到大排序，它已经从小到大排序了。然后这个 vector， 因为 Poisson process 是个 counting process， 它 count 什么？每一个 step 当一个 event happen 的时候，比如说 number infection， 对。然后我现在就把它画出来，就这么简单。然后我说，如果我 care， 我说在这个 small community 有10个人感染的话，就是一个 serious case。我现在 run， 你们也可以试一下。可以看得到吗？线上的同学和老师可以看得到吗？这是我现在 over 7 days 我做的这个 simulation， 然后这是这个是 T1， 你看从这儿看啊，线上的可能看不到，这是 T1， 这是 T2， 这是 T3， 它那个 time， 因为它是什么？它是一个 random variable， 所以它的长短是不固定的。但是是从哪儿呢？是从 exponential distribution with parameter lambda 来 generate 出来的。对，然后 它事实上这个我现在画的不好，因为我是用 star case 画的。我们记不记得它有个 circle？我们之前我授给过大家，它每个 jump 的地方它是什么？它是 right continuous，这个有 circle 的。在拐点在jump 之前，因为 jump 之前是相当于是在这个event 的 infection happen 之前，它是 open circle， 直到这个新的 infection happen， 它就 jump by one， 对吧？然后那就变 close circle。所以我现在没有画出来这个，然后这个就是一个 simulation， 只是一个 trial Boston process。我是说，现在如果我 care 在这个 small community 有10个人感染的话，我就要小心了。我就发现大概4、5天的时候，这件事情就发生了。这只是一个 simulation， 你们跑的结果可能跟我完全不一样，因为这是 stochastic。你看我再 run 一次，有没有？是完全不一样的。所以要做这种 simulation， 你要想得到一个 statistic， 最廉价的方式，就无非是你 run 100,000 simulation， 然后你就能得到你想要的 statistic。比如说你想说什么？如果你的 disease threshold 是我 care about threshold whatever you set up，say is 10， 那你会 care 多久多快这件事情会发生，对不对？那现在这个每一个 trial， 你看 run 出的结果都是不一样的。这个看起来是不到4天，好像或者4天多一点，刚才是4到5天，也许你 run 的可长可短。这个你们每个人可能看到的都是不一样。但是既然你 care about 这个 statistic， 你就 run 这个 simulation， 然后 record 那个 time， 把它都 collect 起来，然后你就知道你想要的对 statistic， 然后你可以画出它的 histogram。大家都知道怎么给定 data 怎么画 histogram HIST， 然后把那个 array 给出来，它就会画出，然后就可以看出它的分布了。当然你可以找出它的 mean 啊，mean 啊 ，standard deviation 啊这种 statistic。这样清楚吗？好，那我们再看一个例子，有没有 any questions about the first example Poisson process？
There are some papers
Yeah.
read the data from this stochastic.
对，这不是 data fitting。The data fitting for this case is super simple. If you can tell me on average, each day or each time unit, how many new infections, that's lambda. I can generate this super easily. But you can do that from the data.
Oh.
Does that make any sense? I'm saying if you can tell me on average,
Like-
say each day as a unit, how many new infection you're going to expect. If you know that, that's lambda. That's it. You can do it. See that? You're trying to say something. Huh? You're trying to say something.
My only query.
Yeah.
In general, in
Yeah.
epidemic for
Yeah.
it goes like this.
Yeah.
Very small in the beginning and then goes and then up.
Yeah.
In this case, I get rapid increase
No.
in the beginning.
This is this is not a whole process. I'm saying I'm assuming in the small community, and I'm trying to capture how things launching up. This can only do the counting process is the cumulative. You're going to count how many new cases going to happen like this up to 7 days in my this
Oh.
my simulation. That's 12 infection.
This is the cumulative.
Yeah. That's right. So must be non-decreasing. This is a counting process. And the key for the problem you talk about to estimate lambda, you can do that from data, right? Yeah. And so now here's a couple questions. So here's the first question. What's the probability? And what should I say? This one is even. What can we tell? What's the expected outbreak size or expected infection size? You know, the process we're considering the Poisson process. Lambda equal to 2 new infection per unit time. That's what we're assuming, right? And now say, what's the expected number of new infection? We know that. We review those general idea. What's the mean of Poisson? 1 day is lambda, 2 days, 2 lambda, so lambda times t, right? So that's the expected new infection. So the expected new infection up to 7 days will be, what's the expectation? So suppose lambda equal to 2, t equal to 7. So it's 14, right? So you can do that. And then, of course, you can tell standard deviation. We also calculate this. Do you guys remember? The variance also is lambda t of Poisson process. So the standard deviation will be something like that. First part, it's too bad. This probably will be only part of the board we can use. Do you mind if I erase it, even you just see this? Okay, any questions about this? This is just expected infection because we're assuming N of t is number of infection at time t. Okay, a second thing. So what's the probability after 7 days you exceed, say, threshold? Now I even make it better because I'm trying to do, that's 10, and you can change that to be 20. You already know the mean is what? 14. 14, right? The mean 14, we just did that. So what's the probability for this to happen? We know because this one follow a Poisson process. So we know how to compute this. Probably might be easier to compute this, right? You guys with me? So we know the probability for each of those is E lambda t. So t is, so 14 lambda 2 power k, k factorial, k from 0 to 220. So this is the PMF for Poisson. We're adding up everything up to 20, we can calculate this. And of course you can do this, but I don't like this. The point is, if this number is big, I have to do this calculation, say 21 times, so many times. Is there any other way we can do it? We can do it. We can use something called central limit theory, because we can approximate, as this number getting big, approximate this by what? Yeah, by Gaussian. Or you can try central limit theorem approximation. It's the only approximation. Let me show you. So here, and the point is, N7 is, this is the Poisson process, is what? Is behave like what? What's the mean? You guys might be confused. It's a normal distribution. With mean, because lambda t is set 14, and variance also is 14. So we're going to do normal approximation. How to do that? N7. Does this make any sense? I didn't do anything. I just subtract mean divided by standard deviation. Now you can see the approximated result is this. Pretty good. But either way, that's not the punchline. The punchline is Poisson process, the simple counting process, could be pretty useful. It's counting something happening, number of events that occurs during a certain period of time. All the key point you need to know is per unit time, what's the average number of occurrence of the events? If you know that, you can do this. Okay, any questions about Poisson? If not, shall we try one? Not this one. Let's try the simple one. This one we just did. Can you guys open the code called DTMC simple SAS? And so now let's see this. Here is again, I clean up all the background. And now B, remember B is the transition probability from S to I. D is the transition probability from I to S. And N, it's okay. So 100 is the time step. So here is, let me show you 10 steps first. So here is the transition matrix we just defined. We saw this before, right? Yeah. Now here is the initial situation. Now I assume X0 is 0, meaning, and the people is, this guy is susceptible. Now, for loop is to doing the iteration. Now I just do this, repeat this step by step. This is what? This is saying you generate a random number that's uniformly distributed on 0, 1. RND, this one. Uniformly distributed on 0, 1. Because I'm trying to do what? I'm trying to create a coin, and I can have probability B to generate a hat. How to do that? So if R is the number I generated uniformly from 0, 1, if this number is less than, say, P to 1, which is B, what? Then you become infected. You change from 0 to 1. Otherwise, you stay at 0. And then, likewise, if currently you are infected, else you are infected, then in that case, I compare this one to P12, the D. And if R is less than this number, basically you using MATLAB to generate a pseudo-random number from 0, 1. Let's do this. So this is something I want to show, because you guys going to do. Oh, I didn't talk about the uniform. You guys know what's a uniform distribution? So the PDF. Oh, the uniform 0, 1. X between A and B, and 0 otherwise. This is the PDF. The flat, uniform distributed. If B is 1, A is 0, that's 1. Anyhow, uniform distributed. If I use MATLAB to randomly generate a number, suppose B, here's how big B is. If my number lie into this region less than B, okay? So you basically using MATLAB to mimic you generate a random call to see what's the probability you less or equal to B. If you're in that case, you do that. Otherwise, you do the other one. The R equal to R A and D, I believe, is uniformly generated a pseudo-random number, not a purely random. A pseudo-random number which is uniformly distributed on 0, 1. If you draw a lot of, I can show you this. If you draw a lot of this R, you will see histogram is like flat, pretty flat. Now, once I did this, once I generate this number, if this number less than or equal to B, meaning I mimic an event, I flip a coin. What's the likelihood I'm going to see head? If the probability head is B, if I less or equal to B, so I mimic this. Otherwise, I'm in the other room. So we're going to use this idea not only for DTMC, other stochastic process as well. So you got to know, use MATLAB, how you could generate this. Or how could you mimic that? So once we have this, we can easily to plot the trajectory, see the result. 10. Because I only do 10. And you can see the transition. If you want to see a better picture, you can uncomment this. Uncomment that. So that's basically showing you how the transition between susceptible infected, suspect infected, and this is just one simulation. Okay, give you the idea. That's all for today. I think I almost ran out of time, and that's all for today. If you have any questions about class, the code, or anything related, and also I know this is not a regular course. You guys not enroll in anything. There's no commitment and requirement. But if you're interested in doing some project or even a mini project or some project together, you could feel free to talk to me after class. And also I'll be staying here until March. So if, you're interested like doing something related to the course, I'm more than happy to talk to you. All right, that's all for today. Thank you for listening.